Okay, we're going to get going. So it's good to be back home again after being in orbit for about 10 days with, hey everybody, with NIPS. I think it was fabulous. I know a bunch of you were down there with me and others, Susan, and we had a whole gang down at NIPS. Various parties and dinners, some of which were hosted by us and by other competitors. On Monday, we had the Partnership on AI board meeting, a full-day board meeting last week that went quite well. It was the coming out party for Tara Lyons, who's the new executive director. It was good to see her take the reins of the organization, which is now standing up working groups. Let's see. So we have a few announcements. So Dan Weld started. Is Dan in the audience? I didn't see Dan today. Dan Weld started as a visiting researcher this week, and he's working with Patrick, I think, to start with, but also mentioned, I think, Patrice and other folks he's interested in touching base with during his sabbatical. Bruno Abraho joined on Monday. He did his PhD work at Cornell with Bobby Kleinberg, and then was at Stanford for a year with Karen Cook and others. And he's interested in exploring mathematical analyses of social phenomena and social graphs and so on. And I know there's we're hoping that he takes up some of the sparking wires from a project on avocado data, looking at tasks in large organizations. But I'm sure you'll come up with many different projects as you think through the year and things you can be doing. And you all know from the announcement that Dean joined formally on Monday, and he's really already been in many meetings and moving things along. And speaking of NIPS and interpretability, here comes Rich Caruana, who was on a panel with Patrice. And it was funny, I couldn't make the panel because of a conflict, but I saw on my Twitter feed somebody very, very excitedly quoting Rich, responding to Jan LeCun, saying, "Yeah, you can have it, Dan. We just announced you're being here. We can have non-expressivity, but you'll kill a few people along the way if that's okay with you, right?" Something like it. It became a Twitter meme, which is nice to see. Let's see what else is on the list here. So we probably just move right into our speaker today, and it's Xiao Dong, who will be speaking on his really interesting work with his team on attention mechanisms. He's been doing a lot with attention models and their use in deep learning and also in generative adversarial networks. So Zhao did his undergrad at Tsinghua, and then he did his PhD work, which I didn't know, at the University of Missouri, Columbia campus, in 2003. And he actually came to Microsoft Corp and joined the speech group with Phil Oliva, NXD at the time. Then moved into MT under Bill Dolan's team at the time, and through Li Deng into the deep learning world that he's in now. So why don't we just move right into your talk?
Thanks. Yeah, so today I will talk about some of the work in multimodal intelligence, more about language and vision. So over the years, we have a lot of collaborators working together on these problems. Actually, we can trace back to 2013 when the first time we proposed a SIP project to work on joint representation learning across language and vision. So that's can be viewed as a start point of this multimodal research. And I will be a little faster because I was told we have to finish everything in 1 hour. Let's see. So the outline of today's talk is about what we want to do. So eventually we want to do this multimodal intelligence can be viewed as we can empower this intelligent communications between human, between computer and the world. So we can use this technology to enable next generation scenarios such as chatbot or mixed reality. And of course, there's many technical challenges. For example, how we can teach machine to perform the true perception, reasoning, or generation, and across language and vision. So to push this research forward to attack these technical challenges, actually the community defines some concrete task or benchmark. For example, image captioning is one of the benchmark. That means how we can describe the content of the image in natural language. And another benchmark like visual question answering or even visual dialogue. That's usually involve reasoning across both language and vision content. And the more recently, people actually start to attack another problem, see how can we generate an image from scratch given the natural language description or called image synthesis. And behind all these tasks and technologies, we also found attention model is also a very interesting model and can be applied to many of these problems and produce a lot of good results. For example, this attention model not only provides a way so we can represent the structure in this problem, but it actually also provides interpretability in certain sense when we perform these AI tasks. Let me give a quick introduction. What is multimodal intelligence? Actually, as a human, we do multimodal learning every day. Because as a human, we learn our knowledge from all kinds of sources. We read Wikipedia, for example, we learn who is Barack Obama. We also, view his pictures. We see his pictures everywhere. And also we know there's a more structured knowledge representation about Obama and his connection to other place, to other people. So if we want a machine to be as intelligent as human, probably we also want to teach the machine to gain all this knowledge from different sources jointly and even perform reasoning, inference across multiple modalities. So let's start with one simple problem like called image object recognition. Vision is, of course, one of the most important modalities, and the people have witnessed dramatic improvements in the last several years in computer vision. For example, just like 7 years ago or even 6 years ago, the error rate on the standard benchmark ImageNet, which is like 1,000 category classification problem, the error rate is still way beyond, go beyond 25% error rate. And then in 2012, as the first time, Toronto group introduces AlexNet, which have a 7-layer convolution network, and cut error rate from 25 to 16. And the people actually at that time even think it's impossible and checked the results several times to make sure there's no overlap between the training and testing. But that turned out to be true, and that's just actually the start, not the end yet. And in the next several years, actually every year, relatively, we can cut the error rate by almost 1/3. And at some time, actually people even check the performance of a human on this data set. I think they found 2 or 1 Berkeley student and performed some tests on the data set. And that student, it's supposed to spend many time to actually classify the images. And he actually achieved like 5% error rate on this data set.
Wasn't the problem there also definitional issues that came up, as I recall? It wasn't just like I can't recognize something. It was like, what bucket you put this thing in.
Yes. So
how much was the student paid for every correct answer?
Okay, that's really the problem. Yes. No, unfortunately, I think he's a volunteer. That's probably the reason. Yeah. Basically, we count the top 5 accuracy or top 5 error rate. That means you can propose 5 possible labels, and as long as one of them is correct, it's read as correct. Yeah. But anyway, so machine actually from Microsoft. The model from our colleagues in MS Asia invented this residual network in 2015, which the first time bring the error rate down lower than the human performance. That was 3.5% at that time. And it actually can be even improved a little bit. So you can see 2.99 in 2016. And this year, 2017, is the last year actually we have the evaluation. The society have the evaluation on this benchmark. That was 2.5, I remember, something like that. And then people think this database is kind of like reached the saturation point and was retired. Yeah. So you can see there's so many dramatic improvements in image recognition, at least in this well-defined constrained task. But actually, this is not the end of the computer vision. Actually, understanding the world is actually much more challenging. For example, for this picture, it's not just about a dog or a woman. It's actually somehow talk about a story. For example, you can see like a woman is playing a frisbee with her dog, and there's many different ways to say that. So this presents a new challenge: how we can describe a thing, a more complicated thing, in natural language. That means you have to understand the content. By understand, I mean you need to recognize the key object and also understand the connection, the relationship among these objects and the concepts. And also you need to generate a story in natural language fluently and grammatically and understandable. So this presents a lot of problems, not only for modeling problem, actually also present the evaluation problem as well. Because it's not easy as recognition, you can tell correct or not. Here you probably have to do something like a Turing test to actually tell if the caption is correct or not. For example, this is a picture, and I give two candidates for captions. And I tell you one is from the machine, another is generated by the human. And as a standard Turing test, I can ask, say, you, the judge, tell which one is more like is actually the human caption. How many have seen the first one? How many of you think the first one is from the human?
Which is which? What?
So for these two candidates, one is from human and one is from machine. So how many of you, as a judge, human judge, think the first one is come from human? Okay, everybody think it's come from human, even so.
Well, the second one is not accurate. That picture does not show anybody playing a tennis, obviously.
That's actually a very good point. Sometimes actually, the first one is from machine. I'm thinking.
The second one is literal. The first one's literal, and the second one is false.
Yes, maybe machine is more literal. I don't know exactly why the human writing like this one.
But you don't know it.
Humans are not necessarily good observers.
The first one's it's just
That's another reason, yeah.
it's accurate, but literal.
Yeah, but actually sometimes we found that when humans describe pictures, the picture from very different perspective. I will show you.
Exhausted.
Is it a human or is it mechanical Turk?
That's a very good question. Shall we treat the mechanical Turk as human? Yeah, I think so far we still treat the mechanical Turk as human. Yes, it's from Turk. Yeah. So, yeah, actually, when people talk about image captioning, there are multiple paradigms. Roughly they can categorize into two categories. The first categorization is like motivated by the sequence-to-sequence machine translation system. So Google and other people propose this so-called vector-to-sequence algorithms. The input is a picture. Then you go through the deep convolution network. You use the last layer, actually the second to last layer, as the semantic representation of the image. Then you feed that vector into a recurrent network like LSTM, then to start to generate the caption word by word. So we can train this also end-to-end by minimize the coarse entropy to train the LSTM. So Microsoft and some other fewer people actually take another approach called Compositional Framework. It takes 3 steps. We detect the key concept in the picture first, and then we generate the candidates from all these all these detected words or detect concepts. And at the end, we build a deep semantic similarity model across both image and the language to measure the global match between the image and the caption and pick the one from the candidates that describe the image the best. So here are more details about the model. For the vector-to-sequence approach, so it's like, in the right-hand side, the image goes through, the raw image goes through the inception network from Google and generates the representation vector, the Bayesian representation vector. That vector was used as to initial the first layer in the STM. And then the STM tried to predict the first word based on the probability. And then the generated first word is used as an input for the second step. And then, like for example, the first word will be S1, and S1 will be used as an input for the second step. Then, as a second step, the STM will move forward to generate the second word, P2, and S2. And then S2 will be fed into the third step of the STM, and keep going on until the STM generates a special sample called end of sentence or a period, for example. So in training, you can just train the whole data. Because in training, it's supervised training. You have the picture and you have the ground truth caption. You just train your STM to minimize the coarse entropy on the training set, on the language part. And in the compositional approach, we actually detect the word first. As you can see in this example, we can detect the woman, we can detect the camera. Sometimes we make some error. We actually detect a cat, which is just the curly hair of this beautiful woman. That's okay. We just over-detect. We just keep all the options. Then in the second step, we generate a lot of sentence. We try to put these keywords, these attributes, into a natural language sentence, which are grammatical correct and also fluent. And then you can see this language model try to describe or try to organize these keywords from a different angle and to describe this picture from a different angle as well. And some of them are correct, some are wrong. And some of them are also biased by the error in the detection step as well. That's okay. So as the third step, we build a multimodal semantic model to re-rank all the possible, to re-rank these candidates given the image as a say query or as a reference. So we try to find the caption candidates that are semantically globally match the semantics in the image. So let me dive into a little bit of details of the model. So first, how we detect the text. We actually try to use a noise-all classifier, treat the whole thing like a multi-class classification. But instead of just generate the text, we actually build a sliding window to scan over the picture and create 12 by 12 like overlapping regions. And in each region, we try to detect if this region contains some particular concept. By doing that, actually, we can detect if the whole picture, what's the probability of the whole picture contain a particular concept. Let's using the concept sitting as an example. So sitting is a particular virtual concept here. It's not a concrete object, but you can imagine it. So when we scan over the whole picture, some of the window will cover a particular area which actually have the clue about a sitting action. And then if you stack all this activation together, you actually get a attention heat map. And in this example, you can see the attention heat map for the concept sitting get almost the peak value at the location which is had here, which is actually corresponding to the pose of the sitting.
So just to be clear about this, do you run this on a particular layer, or on the whole vector? What do you run this over, this summation?
Yeah, so let me show, next page actually show that. For example, this is the whole picture, and every time we have a window to scan over. So in this particular case, this window didn't cover the sitting pose. So the probability of sitting given this particular region is very low. But when the window starts to move to include the sitting pose, then the probability of sitting in this particular region, for example, next step is here. Next step is we'll move to here, and move to here, and move to here. So when we move this way, the probability that this region contains sitting this pose will get higher and higher.
The pose is associated with the word sitting?
In training, we treat the caption. Yeah, that's a sitting in the caption as a reference. So in training, you have a picture, and you know there's a sitting word in the caption. The thing you don't know is you don't know where it's sitting, because there's multiple pose, multiple objects in the picture. That's why when we do this noise-all computation, you can highlight the part which actually connect to the sitting concept.
How are you combining the probabilities of sliding windows?
There are a way to do that. For example, this is the way we compute. So if you compute the probability of a particular word in a particular region, then 1 minus that probability means this region don't have it. And you time together, that means this whole picture don't have it. And then 1 minus this probability means this picture have it.
Yeah.
Okay, so let's go to the language generation part. So actually in here, we use a simple language model. We use a traditional language model called maximum entropy model. People today use LSTM or many other deep learning language model more often. But we found actually sometimes if you care the diversity, if you care less about the accuracy, because we have another module in the later to filter out. So in this step, we more care about the diversity of the caption candidates. So actually we use a traditional n-gram maximum entropy language model to generate to run the beam search to generate 500 candidates. So this language model basically takes the detected keywords and try to organize them into a fluent language sentence. And we don't ask the language model to take into all of these keywords because we know in the first step we over detect the object. So we encourage the language model to take some of the attributes we detected in the first step, but don't require the language model to have to consume all the attributes detected in the first step. So all these weights will be trained using a linear model, actually, to just generate 500 candidates using beam search. By the way, a benefit to use a maximum entropy language model is it runs very fast using beam search. If you use STM to generate 500 candidates, it's actually very slow. So another model we try in the third step is we need to bridge the gap between image and language, because in step 1, we only look at the image to detect the keywords. And in step 2, we only look at the keywords and generate the language. We don't look back to the image. So the step 3, we actually look both image and the caption candidates, and try to find the best one, actually match these two together. So the input is like an image, then you go through a convolutional neural network and get the high-level representation for the image. Then that image feature will be fed into another neural network to further project that image feature into a common semantic space. That space is actually across both image and the language, because in the language part, in the caption candidates parts, we also use, say, a convolutional network to try to distill the semantic meaning of that sentence. And eventually, both the meaning of the sentence and the meaning of the image will be projected into a common space. The model is trained, both those two branches of the model is trained together to ensure actually this, they will be both the image and the language will be projected into the same space. So once the model is trained and once the space is constructed, we can compare the semantic similarity between the candidate caption and the image by measure the, say, cosine similarity in that space.
So when you went to this model, how did the accuracies compare to the original compositional model of the pipeline of the past with the COCO score, with the blue scores and so on? How well did it do?
So this is the third step of the compositional one. The compositional model for Microsoft actually have 3 steps: the detection of the words, the language model generation, and the re-ranking using this model.
This is how re-ranking was always done this way?
It's always done in this way for us, yeah. And if we compare the blue score of this model to the vector to space approach, we can show some number later, actually. And also, we compare blue score, but we actually care more about the Heyman evaluation, just like the Turing test we have done before. Yeah. I will show some interesting results, including the Turing test results.
So
and this is the model also shows.
Question.
Yes.
So in this case, the verb holding is just hallucinated. The image processing didn't actually see Nadal holding the racket. It was imagined by the language model.
Not necessarily. Sometimes you can potentially detect this region as a holding pose, just like a sitting. I mean, sitting is not an object, but actually you can detect.
So you do have a holding detector as well.
Yes. Yeah. Yeah, please.
But presumably you don't have the detector. So you're putting in some words that aren't detected by the vision system. So there must be some trade-off between the language model and putting in hallucinated words.
That's true. That's true. Actually, in the previous slides, we show the language model sometimes will decide to insert a word which is not in the attribute list detected, just to make the whole sentence grammatically fluent. So there must be some trade-off, and the trade-off is trained as reflected in the weight of the maximum entropy language model. Yeah, the maximum entropy model can be viewed as a huge feature set, each feature associated with some weights. So those weights have the balance between you have to use one detected or you use one in your language model's vocabulary, which is not detected in the vision model. Yeah.
Is there any way to iterate this so that the language model actually influences what you see in the image? I mean, knowledge of actually playing a game or holding a racket.
That's actually a very good question. I have one example I can show you, and I see some example there.
But the training is task independent, right?
Yeah.
But so what you're suggesting is it could be kind of task or context
You can
dependent.
iterate,
Yeah.
hopefully, so that you can really have an integration. Right now, you're just having interpretation,
Yeah.
right?
Right. So you can think this way. For example, there are some objects I will show probably in one example. There are some object by itself is very small.
Sorry, I was saying that the previous example was interesting because it showed that the woman was holding a camera, but the detector showed a man behind her holding. So
Yeah.
she was not the one doing the holding, although she was. So it was a bit of a not true
There were two
multimodal
women holding cameras in
integration.
that picture.
That's actually a good observation. Actually, I'm glad that you see that part. From that particular example, you're right. The holding is not detected for the actual woman who we described.
So this reasoning that happens on the image and the concept detected could be taking place, perhaps.
But actually, I mean, look at the heat map. The actual one is a heat map. The heat map is soft.
I see.
Yeah. So the box we draw there is like yes, we choose a box, but you have to cut a threshold. But the one the computer really take is actually the soft score from the heat map. Yeah.
I ask, how does this pipeline, this DSSM fit in the pipeline of the Microsoft your architecture? Where's this piece?
Re-ranking of the sentences.
Yeah, that's the ranking of the sentence. For example, step 1, we detect keywords. Step 2, we generate 500 candidates.
Yeah.
Step 3, we run this one. This is the input. In that set, there's 500 of them in the text set. Each of them will compute a cosine similarity, and you pick the one with highest score.
I see.
And plus a few other features, actually, not just the DSSM. There's 5 other features plus the DSSM. Yeah.
Are you pre-training the language model, or is it just train end-to-end?
The language model in the previous slides is trained jointly with image as well. We need the conditional on the image detected attribute as well, not just the on language part.
Yeah.
So let me move them.
It was trained from the labels on the images?
The language model is trained on the caption label of the image
Okay.
and the detected keywords from the image.
Okay, but not natural language or corpora or anything else.
No.
It's really very image.
Yes, just
Section.
caption right.
Okay.
Yeah. For 2 reasons. A, the style could be different. The language style different. And B, we also want to conditional on the detect attributes. For many other data, we don't have this detected attributes. So yeah, sometimes actually we also collaborate with some people in the vision group, innovation product group. Actually, Lei Zhang, for example, he was in MSRT, but later he moved to the vision group. Anyway, so he had been working on this celebrity recognition, for example. So we try to not only just describe what is happening, a man is working something. Actually, we also want to know who that person is. Sometimes, so we integrate their say celebrity recognition model. So now for this picture, actually, we not just see a group of people posting for a picture. We will see who exactly they are. They're actually the Obama's daughters and his wife, and also the first lady in China. And I think we probably missed one. I think that's the mom of Michelle. Yeah. So that's the caption when we integrate the knowledge as well.
Her mother.
And then in 2015, there's a competition called the Coco Image Caption Challenge. And they eventually actually decided to use human judgment as the final metric. So in our development, we use Blue Score, use CEDA, we use many other things like SPICE. I think Peter this morning gave a talk. But actually, in the true evaluation, we still trust the human eval because evaluation of the language quality is so difficult open problem yet. So in this case, we can we show, for example, we can rank the system by how many times your system can pass the Turing test, or how many times you think your system generates a caption equal or better than human. So these are slightly different metrics defined by the organizers, and they kind of like correlated with each other. And in this case, I think Microsoft and Google tied for the first place officially. Yeah. I think that's, yeah. And even more interestingly, actually, the organizer also include a so-called human system. The human system is just ask another human to write a caption, and then ask a judge. Of course, don't tell the judge this is a human. Just tell the judge to see if to perform the same Turing test. So interestingly, even the human cannot pass the Turing test 100%. The human can only pass the Turing test like 2/3 of time. So this back to the original one, the Turing test we just done. So people have very different view on the same picture, and we describe it very differently.
Some of these human-generated captions from Turk and with typos in them. Like, wait, I know that's human. So.
Okay, that's good. So we can mimic some typo as well in Turing test. Yeah, please.
Wait,
Yeah.
so is Turing test for?
Sorry. Okay, let's see. Paul, go first.
Do you know how much of that comes down to knowledge that's expected to be demonstrated? So, for example, if you had an image of Trump it would be unusual for any human to not refer to him as Trump, to call him a man, blah, 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 blah.
I see.
Right? And this is one of the things, there's sort of an expected common base of knowledge that people expect from humans.
Yeah. So in this case, when people create Coco, the people try to avoid include any significant object or entity. They try to use. They try to exclude all the possible entities people can recognize. So regular people, regular object, regular things. And when you write the caption, also the Turk at least is be indicated to don't write out the specific type, specific number, or specific name of this one, rather than use some generic way to describe it. Yeah.
So I think maybe beyond this, maybe the way you want to do captioning should be different. It shouldn't be that humans should describe the image. It should be say something about this image so that you would pass the text, so that another human would see that it was a human who talked about it.
You mean in the test, in the Turing test?
When you're making labels, because all these humans could have made labels so they would pass the Turing test. If you told them they were going to be passing the Turing test, then they would make sure to convey the message to the grader that they're human.
That's true. That's probably true. But actually, when we collect, not me, actually, I think Larry and his team, when they collect the data, the specification is you try to write the things in a generic object level of vocabulary, rather than too detailed, rather than too specific. Yeah. Yes.
Speaking of Bosch's comment, I mean, there were follow-ons that, like Meg and Larry were involved with that did more human-like things. So the work I thought was particularly interesting came out of discussions that were kind of more or less obvious that when people describe a picture, they don't just necessarily give a factual listing of all the objects. They actually will talk about the interestingness or the focus of attention or the anomaly in the picture, like a gigantic yellow ball being held by a toddler. They'll say something about the weirdness, and so they did a paper on that would filter these things by the focal focus, the anomalous focus of attention, or what a human being would focus on. Right.
Yeah. Yes. Okay. Sorry. Okay, Matt, and then.
Sorry, can you explain a little better what it means for a capture pass the Turing test? Because I would think it would only get 50% if the human. Does it mean that they correctly predicted which one was human, or?
No, I think by definition, Turing test says if the judge cannot tell, if judge tell the computer as a human, or judge cannot tell which one is human, that is viewed as passed. So ideally, for example, for this case, the judge will keep saying, I cannot tell which of these two are from machine. So that's why the upbound is 100%.
Okay, so they have three choices.
They have three choices. Yeah.
Okay.
A, B, or cannot tell.
I see.
The judge is presented with only one caption and wants to tell whether it's human, machine, or
no, it's two.
Or
the
two.
Picture and two caption. And then the judge asks, A is human, B is human, or cannot tell.
Okay, so essentially the tests for human and MSR, Google, etc. are different in that, like the result caption from our system is paired with the human caption, right? And
compared directly.
whereas for human, it is paired with the machine caption.
No. Even for this one, for human, it's still against another human. You can think there's a system called a human, and there's still against with another human. So in this case, the judge will be present a picture and two captions, both come from human, from different human. Of course, the judge didn't know. The judge just think one is come from machine, one is come from human. So if the judge if everything is normal, then the judge will think they cannot tell which of these two come from human because they're equally like human. That's what we expect the judge will see. In that case, we think the human system passed the Turing test, and suppose it shall be 100% pass the Turing test because every time suppose the judge will think they both cannot tell which one is machine, which one is human.
There's an inherent flaw on this that at least I see on the personal level. That the stimuli is very different for the human than for the machine. What was the human told to say? See an image and describe it in your best words, or whatever stimulus you love, versus what you tell the machine as instructions. It's really, I will claim it's not the same you were told, one or the other subject. Henceforth, whatever outcome you get, it's going to be different. It's like having two humans and you give them two different sets of instructions. They're going to label things differently.
That's true. So the labeling is done. Actually, this human is nothing special. This human is one of the Turk as well. I see. They all read the same specification.
My ultimate point is that I think the Turing test is a misleading ruler. for measuring things here?
You can argue with that. Actually, they have 5 different metrics, but there is still
Fair enough.
this is already. Let's see. If you look at blue score, you'll be even more surprised, or other score. For example, if you go to leaderboard today, there are more than 15 different systems claim they have better blue score than human now. So this kind of evaluation, given the specification is there as we provided to the Machine Turk, give this constraint, this is a test. Let's see. Yeah. It's not the original Turing test proposed by Turing, of course.
I've been proposing to Zoe actually to do the Turing game, where people are talking to each other and then Zoe is intervening and you don't know whether you're talking to a human or not, and they're labeling each other and so on. But you could run something like that here, so like a Blade Runner Turing game.
But for
That
Zoo,
might-
you can also argue, for example, in Zoo, you never speak things like this, right? Like a man is holding a rock in the in the social network case. You may speak
That's true.
different style.
That's true. It will be much harder with images than with text. But still,
Okay, probably we shall talk offline because I think I'm totally wrong about that. Yeah. So let me quickly finish some other interesting stuff. So yeah, thanks for the interesting comments, and I want to show you some dynamic attention map we generated from the examples. For example, given this picture, the caption generated by the machine is a baseball player throwing a ball. Sounds very interesting or sounds very simple. Actually, there are a lot of things in the behind the curtain. For example, why the machine think it's a baseball activity rather than some other sports? Because actually, if you look at the attention map, the machine focuses on the very special glove for this player. That part makes the machine think this is a baseball sport, baseball game, and rather than say basketball or some other activities. So the machine also focuses on other parts and detect and tell this is a player. And more, for example, throwing. Throwing is also another interesting pose or action, which there's no specific object. But actually, the machine learns from multiple data and can focus on the twisted leg and infer there are throwing pose here. The arm could be another example. I mean, that's what I showed the machines focus on. Actually, I'll show another example even more interesting.
Throwing, the player was also an odd thing. They focused on the elbow rather than the number.
No, actually, the player cover everything. It's pretty much. I mean, you cannot take this literally. I mean, it's kind of this whole region. It has reasonably high scores.
What do humans look at?
I mean,
When you asked them if this was a baseball player throwing a ball?
Be to the extent of gaze tracking.
Through gaze tracking for humans?
Yes.
Well, what Susan's suggesting is we can do a gaze study and see how they line up with the
Okay, that's another interesting one. How the true attention from human actually is aligned with the machine attention. Yeah.
And we see them looking at the thigh for some reason when they throw.
Yeah, and this is another example because someone asked, could the language model help to detect some vision content? This actually could be one example because if you look at the ball is very small and weak, and you cannot really tell it's a ball. So, but the ball is so important in a sentence because that's complete the semantic meaning of the sentence. Let's give some boost to the system to look for this particular place and boost up the value. And then, for example, they boost up the language score for this particular candidates, and eventually output the ball here. And here another interesting example. The interesting thing happened in the first word. So we say a man sitting in a couch with a dog. How machine tell this is a man rather than a woman? So now if you draw the attention map, you can see actually the model focuses on the beard of the people, just a beard part of the face. And that actually gives a strong clue. I mean, this is a man rather than a woman. This actually could be interesting because later I tried this caption bot to many of my Asia friends. And many times Asia friends is recognized from man to woman. Actually, many Asia male is recognized as a woman because we usually don't keep the beard. So let's actually give a debugging information, tell why this happens for some people, but actually works well in US. Of course, this is not only the feature. I mean, there are good cases that if you don't have beard, you still recognize as man. But this gives some debugging information as well. And yeah, sitting and the couch and the dog going on. Yeah, and more recently, there's some other model, for example, how we can correct this, can improve the performance and can control the generation. For example, originally 1 year before, we misrecognized this toothbrush as a baseball bat. And today we can get it correct But even more, if we change some particular word in the detected attributes, the whole sentence will be regenerated to accommodate this change from the user. So the user can overwrite the machine's output by just change a few key concepts. So this is done by using some very wide model, not very deep, but actually very wide. We build a model can viewed as like 1,000 STM and combine them together using some tensor decomposition. So each STM can be viewed as two corresponding to a particular attributes. So they work together, eventually generate the composed sentence for the whole image. In this case, for example, we detect a few keywords like snow, like skin, and man, and the slope. So you can think the STM associated with those concepts have high activation, and they are going to run, and together they propose the candidates and generate the final caption. This caption can read as a man riding skis down a snow-covered slope. And more recently, we also start to explore some other directions, like can we generate a long paragraph? For example, given a bunch of pictures, can we use reinforcement learning to tell a story of the multiple pictures? For example, if you go to a party or go to a wedding party, you want to see multiple sentences, and they are coherent, and together they describe different aspects in this story, and come up with a long paragraph. Yeah, this can be done using some hierarchical reinforcement learning models. I will skip the probably technical details. And there are also other trends. So how can we control the style of the caption, make it more humorous or make it romantic? Because for other applications like a zoo, for example, you probably want to generate a more funny or romantic caption, so people actually feel more likely to share this with other friends. And this is done by we disentangle the specific styles from the generic linguistic structure. So we can use part of the model to cover the generic linguistic structure for language generation. And then we can hook up with another style-specific model to control the style. And for example, there are some interesting examples which we try to talk to the Xiaoi's in India team to generate the image comments for the social media. When they deploy the Xiaoi's English version in India, people will share some image to Ru. That's the name of Xiaoi's in India. So you can think the Xiaoi's is expected to say something funny, not just to describe the content. For example, for the first picture, the traditional recognition will tell you there's a woman and a grass. And if you fit this picture in the caption bot, which is designed to describe the content factually, you get a woman wearing a blue shirt. It's perfect, but not fit the social comment scenario. So now actually we developed some new model, so it will return something like gorgeous and beautiful as an angel. So suppose if you share your girlfriend's picture in your friend circle, you probably want the machine will generate something like gorgeous and beautiful as an angel. So your girlfriend will be happy rather than just see a woman wearing a blue shirt. Yeah. And there's other examples. So we try to add some emotion and style in the caption generation. So later this is deployed, actually this is deployed on the cloud last year on build. And this is the API actually many people can call. This API right now is running, and we can provide a service to translate any image into text. Recently, we also talked some business group. If they have needs to understand image, but they don't want to host their own vision group, they can actually call the API to translate image to text, and usually they can use the text processing algorithm to do that after that. Yeah. So there are more examples. For example, this is the picture, and our caption bot will show this is a man flying a kite on the beach. And there's another picture actually I took when I visited San Francisco, the zoo last time. And there's one more actually. This is actually a picture I took when I attended ICML last year at New York. So I have my phone with me, so everywhere I just try this caption bot and see how it goes. And there's another picture, so you can little boy sitting in front of the birthday cake, and he seems happy. So we not just try to do this for fun. Actually, we try to deploy this so people can try, and we can collect data, and we can understand how people use it or how people look at this. For example, when we put this online, BBC actually tried it. sometimes they try it and they make joke of it. They say even our bot cannot recognize another bot, for example. But actually, we collect all this feedback. Yeah, actually, many people try. Actually, I think Phobos also tried that, and CNN and the people tried it. And with all this try, we collect a lot of data. We collect, yes, we collect a lot of data, and actually, it's turned out to be very important because with every time people try, we ask people give a feedback. For example, people, no, not here. People give feedback from 1 star to 5 star. And meanwhile, internally, we will estimate a competence score. Then we check if there's a huge mismatch between our competence score and the human score. Then we know there's something we don't know, actually. So that's the part, especially in the right-hand side in the up row. So there's 10% of caption. We think we're really confident. But actually, user give like 1 or 2 stars. Those parts actually are very precious for way to keep improve the system. And here are more examples. For example, we visualize the different parts. This is, the x-axis is the user feedback score from 1 to 5. And the y-axis is the competence score from 0 to 1. The higher the better. So you can see for the green dot, we think we're doing well, and the user also think we're doing well. Actually, there are the pictures like the common objects or the natural photos. And then for the other parts, even for the lower end, the red dot, although we're not doing well, but that's okay. For example, the user give feedback like 1 or 2 scores. But actually, we know our own competence estimation also gave like 0.2, very low competence. So we know we're not doing well in that part, for example, in this particular part. We know we're not doing well, but that's okay because we can filter them out. We can just set a threshold of competence and filter them out. The part actually worry us a little bit is this part. So user give a very low score, but actually we are very confident. We think the competence score is higher than 0.5. So for this part, actually, that's actually a very good data for us to do some active learning. We spend a little bit of money to relabel some of this part of data, and then let's improve the system dramatically in a short time. For example, here are the involvement of our system. So in 2015, that's when we participated in the competition. Although we are the winning system, at that time for Cocoa, I think our error rate is like almost like 30%. And after just like 1.5 years, given all this new data, given all this refreshment, we cut the error rate also by about half. And more importantly, on the open domain, like office or arbitrary domain, back to 2015, the error rate is as high as 75%. That's almost non-usable. But today, we can reduce this to be about 30%. And then collaborate, and then together with the threshold cutting, if we can set a reasonably high threshold, we can make sure the caption we generated have an accuracy around like 90%, which reach the office bar. So actually, they ship this in office point now.
We've had this discussion, I know, Chaidan. We're still not. How are we using the confidence score in the ship system right now? Are we using it at all to guide it?
Yeah, we use it in such a way. For example, if the confidence score is lower than 0.5, we will not display the caption. Right.
Okay.
Below 0.5?
Yeah, 0.5 is.
And then remind me if I don't recall in the Office version of this if there's a feedback mechanism. Is there?
Yes.
There is also stars.
It starts and not starts. Actually, the feedback is more like you can input, you can correct the caption.
And we capture the correction.
We capture the corrections, so we can keep it and get the new methods.
Yeah.
So today we get like 1.5 million usage every day, so we get a lot of data.
Yeah. Great.
Yeah. So we put it in Office, and we also support the other application like Seeing AI. Saki actually is good friends, and he also contributed a lot to develop this application. And let's go to the next quickly. Next one.
Seeing AI still have the same. It still has good engagement. Continues.
I didn't track closely. Time and time I get some message from Alinu and Saki, and they collect a lot of interesting, actually very good feedback. The thing is, because I'm not a blind people, so I cannot tell how important it is. But Saki tell me, for the people who are blind or vision impaired, they so appreciate any help to help them to see anything. So let's move to question answering. Because we go beyond description, we also want to do some reasoning across both image and language. Here is a quick example. Given an image and a given question, the answer shall be, say, dogs. So it's very simple for human. But what we actually do, as human, actually, we quickly shift our attention because when we see the picture and when we see the question, we probably first immediately focus on the part, like bicycle, like the basket, which is mentioned in the question, and ignore the background, for example. Then we probably further focus on the place asked by the question, like the region in the basket. And eventually we come up with a dog. Actually, we developed some model motivated by this process. We developed a model called, like have multiple components called stacked attention network. In this, first we have a language generation model or language understanding model to code the language into a vector representation. We also have an image model to code the raw image into representation as well. Then we have invented a new multi-level attention model to model the interaction between language and the vision signals. And eventually we predict the answer at the end. So the interesting part is, if you visualize the attention layer in the model after it's trained, it's actually come up with something like this. So it's mimic like the intuition we have. For example, the first layer of the attention model shows some heat map that focus on the basket, bicycle, and things in between. And the second layer actually learn to focus on just a dog and ignore the basket and the bicycle. And this part information give our strong information, the answer shall be a dog. So here are more details of the model. I probably will ignore some details. This is a traditional convolution network. And this is using STM to code the language. And then this is attention layers, layer 1. For example, you start with the image and start with, this is a vector representation of the question. And the up is the spatial feature vector from the image. Then we compute the attention map between the image and the question, and highlight the parts that are relevant, more relevant to the language in the image. And then we generate a context vector, and then do this multimodal pooling and generate a new query or representation. Then we further fit this the new query vector, to the second layer, and do almost the same thing, requery the image again, and generate another image, another attention map, which are more concentrated on the region that are more relevant to the answer. And keep going on to generate a new feature vector. Eventually, this feature vector will be used to predict the answer. That's the answer prediction module. And in evaluation, we can tell this model dramatically improve, particularly in a category called others. This is actually the setting of the visual question answering. You have yes, no answer. You have how many this kind of answer. And also everything else. Everything else is about what's the color, what is that, or where it is. So because the attention model can help you to concentrate on the parts which are relevant to eventually the final answer. So we improve significantly on the other category. For the number and yes, no, we have some improvements, although not as significant. And here is one more example. So for this picture, if you ask what's standing between two blue large chairs on an empty bridge, the model as the first layer will focus on the chairs, which is mentioned in the question. And in the second layer, the model will more focus on the umbrella in the middle of these two chairs, and derive the answer, which is the umbrella. And more recently, actually, Peter Anderson and a few colleagues worked together, developed this bottom-up attention model. Actually, Peter gave a wonderful presentation this morning. So this further improved the performance. The improvements come from, rather than use this uniform segmentation of the image, we can do fast RCNN to detect the object and then extract the feature for each object and then pay attention on the object rather than on the uniform, separate, segmented spatial place. This gave a big boost. I will limit of time. I jump to here. So actually, 2 weeks before the VQA 2017 competition, we get this model done, and this model is originally invented for image caption rather than for visual question answering. So we don't have time to develop a visual question answering system from scratch. So Peter talked to his roommate in Australia, who had been working on this problem for many time for years, and they have a reasonable baseline. So his roommate agreed to take our feature, integrate it in his model, and try a submission. So eventually that led to 2 submissions. One is the Adelaide team, just the pure baseline with their own system without this feature. And this system gives you a number like 16.5 here. I think this is the Adelaide University themselves. That's 16.5. So this system is the same Adelaide University system plus the new bottom-up attention feature. So this single attention feature actually brings the system from number 10 to number 1, and the gap is about 5 points from the system. We don't have much time to actually fine-tune it yet. Given a little more time, probably we can do it better. But this actually simple trial already shows the power of this bottom-up attention model. Okay, so last topic is also probably the most interesting one, language generation. Actually, Eric suggests it's like word to birds. So this is actually the one actually we think is the most fun one, because everybody think you want to be an artist, and you might think you want to draw birds. For example, in July 4th, you want to draw birds like you have a blue wings or maybe have a red belly. So many people will stop there because you don't know how to draw it. It's actually you have to take some class or be a professional to actually draw interesting birds. But actually, we build a system. Given the input as a sentence, you just talk to the computer. Actually, we'll draw this bird for you. This actually is not a bird we search from the internet. It's just draw. It's actually synthesized by the computer pixel by pixel, because you can even tell actually the beak of the bird actually is also blue, which is a little unrealistic. So this is what we want to do. We want to convert a simple idea, which is in a natural language, to a full imagination, just like the birds, as well as like this one, or like this one. So they are all imagination from the artificial intelligence. And this actually is a new, interesting emerging field. Don't have very long history yet. Just last year, for example, in SML last year, 2016, there are some papers using GAN start to do image generation. The idea is relatively, it's not simple, but actually it's very straightforward. For example, you code your language into a vector. Then use this vector plus another random seed together to fit into a deconvolution network. Then you keep unsampling, eventually you generate the picture. And then you fit this picture into a discriminator network, which is another convolution network. And then eventually you want to tell if this image is good in 2 criteria. If this image itself looks like real or not, and also how much this image match the sentence in the input. So the loss actually take 2 parts. So you train all the model together, and then eventually hope your generator can generate some image that can fool the discriminator. And you can tell and you can take a look at the quality of the image generated last year. On the up part is the birds, and on the second part is about the flower. So that's like 1 year ago step art. Yes, Matt.
Just out of curiosity, do people compare against just a retrieval model on the training set?
That's a good question. So depends on how you design the natural language, because there are some descriptions you don't find the picture in the real world. For example, if you want a bird which has blue beak, you probably cannot search anything.
Sure.
So in generally, when people evaluate this thing, we have some evaluation, like you compute the inception score to measure the quality of the generated image. I don't remember that direct comparison with this one and that one is. As I said, it depends on your setting.
Do you have any examples that would blow Matt's mind? these he would think IR, but he show some of the crazy ones with the 2 heads and so on.
Yeah, I will show.
I mean, crazy blowing mind is fine, but but if it's evaluated, if there's a metric and the evaluation, if it's the same sampling of captions as were in the training set, then it's plausible that you could do just as well or better with IR. And
that's the metric, yeah.
I mean, it doesn't mean that's useful, but it means that maybe it's misleading. It could be whatever network is best able to memorize the training set does the best. And
that's why actually we have some study analysis to show it's not about just memorize, and the training is not collapsed. And we have some examples to show actually they generate some normal things. Let me go quick and show you the example. I will ignore probably the equations. So we basically, so this year we actually work, a few people in the DRTC together with interns work on attentive GAN to further improve the performance. And here's the model. So rather than use one GAN or one stage, we actually use multiple stage, and each stage we try to incorporate the attention model. Quickly go through here. So H0 is the first layer, and then it comes from the global language embedding and the noise, random noise. Then in later different layers, your computer attention between the different words and the different region in the H. H is not just one vector, it's actually a group of vectors in the convolution layer. So you compute the attention between the E, which is also a group of word level of embedding, versus a group of region level of vector. And then you compute the attention and compute the next layer of hidden layers. And eventually you can generate the X, which is the picture generated from a particular H. So so you can see we modify the GAN by not only changing the generator, we also modify the GAN by changing the loss function. We could introduce a new attention loss. That means when we compute if the generated image is good or not, we look back to the image and the text and see at that level, at the attention level, can measure the match between the generated image and the original text. Let me skip this one because I don't think I have enough time. So these are experiments. So there are two major data sets. One is the bird data set, CUB. Another is the COCO data set. The COCO is much more challenging because COCO have a lot of different objects. So now you need to train one GAN to fit, say, maybe 1,000 different objects in COCO. Actually, COCO have 80 different objects, but have many different backgrounds, have very diverse combinations. Let's focus on this table. Okay, this table is compared with previous state of art. So usually, quantitatively, we measure the quality of the GAN image generation by the inception score. So for the birds one, the previous best results is like 3.8, and we actually can improve that to be 4.36, which is quite significant already. But the most significant improvement comes from actually the COCO one, because COCO dataset have very diverse background, have very complicated composition of different objects. So you really want to know which part you should put which object there. So attention model help a lot for the complicated COCO dataset. We almost triple the inception score on the COCO dataset. And let's give you some fun example. So here is the example how we trace back to the attention model. We want to generate a picture of a bird have like a green cone and a black premise and a white belly. So that's different level. We have multiple stacks of layers of GAN. So let's focus on it here. So this shows when we draw this region, we want to decide the color of this region. Then we actually look back to the sentence and found black is the word actually control this region. That's why eventually we actually will draw a black color in this wing part. And when we draw this region, actually the model will look back to the sentence and more focus on the green word, because actually they were asking for a green cone, and then make this part actually green. And also for the same thing for the belly. So when you draw this region here, the model will look back to the sentence and focus on the right part, the right word, and actually draw that in the color of white. So that's how eventually the whole picture is drawn at different region will be influenced by different word in the original sentence. And then if we go beyond bird, we go to a more complicated, like a COCO scenario. This is another example. For example, we can draw a fruit standard display with banana and kiwis. And the interesting thing is like here, for example, somehow when the machine draw this particular part, for some reason the machine thinks this is relevant to the kiwi. And then actually look back to the kiwi and I draw a small kiwi here. So which probably, I guess, is this one, if you think it's a kiwi. Yeah. And the banana is also interesting. You can see banana, the color is right, the shape is a little off, but pretty much like there. And there are some other pictures. So this actually is, within 1 year, actually, the picture become much higher quality than last year. So they're all generated from scratch. I mean, input is a sentence and output is a image. And there's more example which go beyond birds and go to the daily COCO things. For example, for the shape, I think head of shape grazing on the large green field is good. Some of them are not that good. For example, there's a floating boat on the lake, if you look hardly. And there are more examples. So, well, sometimes we don't draw this very clearly. It's like go eating a pizza. Actually, when later I feed this picture back to the Caption bot, and the Caption bot perfectly tells this is a woman eating a pizza. I'm not saying the bot is good or it's good. And when I feed this one back to the Caption bot, The Caption model is also perfectly see this is like a clock on the next to a building or something like that. So that's make me think maybe there exists a set of minimum feature set to describe different objects. Somehow the caption bot and the generator agree on. So for example, in the daily life, we know most of the clock are around a circle. That's probably because we make them cheaper, and that's easy to make. But in the digital world, it's equally difficult or equally indifficult. So they just make different shapes. And here are some examples which are not exist in the real world. For example, how a cat can, a black cat floating on top of a lake. You can roughly see there's a lake and something like a fluffy black cat, or a red double deck bus floating on top of a lake. So you can think the machine a little confused and draw something kind of like a bus because you can see the light here, but also kind of like a boat because you put it on top of the lake.
Secret to my nightly dreaming.
Get confused, it's even more. Yeah, this is the one really like a dream. So sometimes it can be like create something like birds have multiple heads, multiple beaks, or very unrealistic shapes out of the mind of the gang, I guess. Yeah, they're all artificial imagination. And there's some other more generation things. This is actually an interesting example. I want to show two things. A, the sentence is almost the same, except we change the color. And every time we change the color, the model can precisely or quickly catch the change and redraw the picture accordingly. For example, in here, if we want the birds which are red and have a yellow belly, all the birds have red wing and yellow belly. And if we just change the color to blue and red, the things all change in the next way. So that means the model can be very sensitive to the input, catch the input very well. And also I want to show actually there's some randomness as well. So when you input the same sentence, you don't always get the same the same birds. Sometimes you get some different birds. That's because the language is underspecified. Language cannot tell every single detail in the picture. So there must be something which cannot be told in the language. Then the generator have to imaginate that part and come up with the missing part like a background or some other shape or the pose and put them together. Yes, Matt?
So, but I think it's interesting that the background is relatively consistent based on the color of the bird. And I'm curious if like do black and white birds tend to appear in brownish scenes and yellow birds appear in green scenes in the data set? So it must be picking up those correlations too, right?
Yeah, that's a good question.
The
actually,
color of the bird tells you the background color.
Yeah. I remember EJ have asked the same question.
Yeah.
Yeah, maybe there's some collaboration subtly catched by the model. Yeah. And we need to probably dig into the model to really tell that. But yes, thanks. That's a good observation. So the last page, we want to show, this is about 1,000 pictures generated by the model. We just want to show the model actually runs very stably and not collapse to a few single example. It's pretty much smoothly cover the space of the bird. Different pose, different background, different color. You can think the space estimated by the GAN is relatively smooth and reasonable. And the same thing for the COCO. So you can see more diversity on the COCO dataset. But still, this kind of show that the model kind of smoothly cover the space rather than just collapse to a few locations. So look forward. So let's back to this picture, which is actually fun. So this picture, if we go to fit this picture to the caption bot, you all see a herd of elephants standing next to Obama. So nothing wrong. It's perfect. But anyone in US, after you finish college, have some background on politics, you probably know a bit more than that. For example, you probably know Obama belonged to the Democratic Party, who actually compete with the Republican Party, and who is represented by the elephant. So with all this background knowledge, then you actually want to see something like Obama chased by his Republican competitors. Yeah. So this is a picture actually created in 2012 I found on the web to actually deliver this kind of thing. And more interesting, maybe we can even generate the virtual question answering and say, can we ask who is that person? That's an easy question. We can find it's Obama. But sometimes if we ask a question like, why these elephants are chasing him, this is actually a much more difficult question to answer. You have to know all the knowledge and actually make it the right answer. And even more interesting, maybe one day we can just say, draw me a picture to showing Obama are fighting with other competitors. Can one day the machine just draw a picture that reflects your ideas from scratch? So you can just become an artist, do anything you want, and express yourself much more efficiently. Yeah. Yes, pretty powerful.
So maybe as a step before the draw me a picture showing Obama, has anyone looked at composing in layers, where you might describe this picture as in the background, it's a sunny day with a few clouds, there's a herd of elephants running, and in front of them, like, so it's very much kind of in layer stages that you're composing.
To my understanding, no, not yet. Maybe there's some work, so-called language-based photo editing. I think some work we presented yesterday from Business AI. They try to say, I want to have a red color of my flower. For example, you have a flower which is black and white. You can say, okay, put a red color on the flower, then you can get red color of flower. This kind of like command and control. And also people try this style transfer. For example, you have one picture from your photo album, and you have a Van Gogh's picture. You want to put these two styles together. This can be done, I think, 1 or 2 years ago. Purely use language to control the content from scratch, even as specific as you said, is still an open question. Yeah. So for that, I make a summary and conclude. Basically, that's what we want to look at. We have some deep learning, deep attention mechanism as a foundation for algorithm. We also try to attack like image to language or visual question answering or language to image kind of problems. And this can serve multiple scenarios. For example, chatbot, digital assistant, maybe many other scenarios as well. So let's pretty much conclude this talk. Thanks.
Questions?
Okay.
Shalom. A really nice talk. So I'm curious, could you say a bit more? I'm curious about the kind of almost like debugging tools you use when you run these experiments. Like how, do the attention models give you insights into, like when I'm imagining you start somewhere and then you evolve the model in some ways to get better and better results. I'm curious about what drives your search in that. Like if you could say a bit more about, do you do error analysis? Does the multimodal, does the language result tell you something about the other guy? How do you kind of evolve and search in the space of models in your experience as a researcher on this?
Yeah, so that's a very good question. I don't know I have a definite answer, but what we do is, yes, so the attention, when you draw the attention map out, you can start to get some sense what the model is looking at, different place. For example, use the visual question answering as an example. We start, when we draw the first one, for example, we say, oh, actually the model really look at different region and use different region to predict the answer. Then later, let's make us think how to represent different region more efficiently, more accurately. That's why I motivate us to do this object detection first, then feature extraction later, rather than do a uniform segmentation and do feature extraction. Because we think the attention map in the first stage show they do look at the regional vision feature. Then making this regional vision feature correct is actually could be important. Then let's make us think how to make it more correct. So let's think, okay, we can do the bounding box first, then extract a feature in the bounding box rather than a uniform segmentation. So this kind of like insight or analysis we have done before. Yeah. But this is one example. I don't know if we're looking at there are more systematic way to develop a more systematic model to do that. For the GAN, it's also the same thing. For example, we believe, because based on our observation in the question answering case, we believe when you draw a very complicated picture, you have to know which part you're drawing and which object in the language actually you're drawing at which place. So you have to build this substructure alignment, substructure level alignment between the input and the output. So that motivated us to invent this attentional GAN. And then we run end-to-end and try many things. Sometimes it didn't work well. We need to check why it didn't work as we hope. And sometimes it works out. Yeah. Paul?
So going just to like the example on the left here, image to language, are people still looking at where there are gaps just with these basic problems? So like in the baseball player throwing a ball, it's going to the most common denominator, right? In fact, that's not any baseball player, that's a pitcher. And that's a pitcher winding up for a pitch, right? He's not actually throwing the ball. It's very specific. It's not an outfielder. It's not an infielder. You can tell it from the image. But it's just, the most common denominator, learning from much data, goes to the most generic description of this image rather than, the most information full about the image?
Yeah, that's a good question. So basically, you see at which level of granularity actually we describe the image. So I would say the machine just learn what people see. For example, because all the Mechanical Turk produce this caption as example to train the model. So based on the specification, this Mechanical Turk, although they disagree with each other, they still provide at a reasonable level of granularity to describe the image. That's actually kind of amazing. So people, although disagree with each other, still kind of agree at which level when you describe some image like this. And that's what we learn. And in the future, actually, there's some new work come out. Can we generate much denser description? For example, or can you generate a much longer paragraph or even generate caption for a video? And then eventually, I would say, still learn from how people describe things. And it depends on your specification of the data annotation, you probably learn at different level of details.
Back to the ESP game, this was a problem there, right? And there were mechanisms that were developed for it. So like one is a 3-player mechanism where you have 2 people trying to agree and one person who, if he manages to agree with them, disrupts them and their score is decreased. And now they try to basically go to a less generic description but still agree, right? So that's like a general problem in terms of labeling that there's been work done, and it's worth thinking about what is the ground truth we want to collect.
That's true. Actually, we try to, for example, later I also start to collect data. I try to see you have to write something like longer than 15 words. So we pay Mechanical Turk, and we don't expect they just say something like 1 picture, 2 picture, or 3 picture. Right? So we say you have to write down something like with 10 or 15 words. Let's actually specify the detailness of the caption probably in certain sense. Yeah. Because Turk just take 2 cents a sentence, so they will not say too much about this picture. They will probably just pass the requirement. Yeah.
I thought that just occurred. Photos are just not photos anymore. They're just like small snippets of video that contain motion, that have strong meaning. Humans are very good at interpreting. I wonder if you're aware of any direction that is using that information as part of the input that all these models are taking. Because right now static photos are great, but you're inferring motion, and having the real motion out there, I imagine can provide you with so much information to be much more certain of what's happening on the scene.
You mean we do video analysis, or you mean we treat the photo?
An iPhone, whenever it takes a photo, it takes a 3-second clip.
I see. You mean a short clip?
Yep. Okay. So the photos have enough information to disambiguate, is that guy receiving the ball or launching the ball? Is the man actually running or just standing? Is the bird flying or not? So there's a lot of interesting information that you can gain from seeing that it will be fantastic if multimodality gets to embrace. I don't even know the state of the art, if that is even in people's minds.
I see. So you can see actually we can detect action even if it is a static picture. I mean, there are many examples. But if you really want to do the action detection or object tracking, like in the video space, actually there are a video caption or video understanding area. I still believe for action detection, probably a short clip is better than a static photo. Does that answer your question?
Motion detection. And anyhow, I was curious because why not?
For motion detection, yes, you can do that in picture, but mostly there are some competition that you detect motion in the short video, actually. There are some challenge in CVPR this year as well.
I see.
So Gonzo, take it off live would be great.
Oh, absolutely.
Thanks so much.
Thanks.